On a humid September morning in 1943, the air above Bougainville hung thick with tropical moisture and the lingering smell of aviation fuel. First Lieutenant Kenneth Walsh sat in the cramped cockpit of his Vought F-4U Corsair, still wearing his flight gear despite having landed 20 minutes earlier. His hands moved methodically across the pages of his personal logbook, recording observations that would later prove far more significant than he could have imagined in that moment. The leather-bound journal, creased and stained from months in the Solomon Islands, contained technical notes that represented the collective experience of Marine fighter pilots engaged in daily combat against the Imperial Japanese Navy's aviation forces. "The new aircraft changes everything," Walsh wrote carefully, his handwriting betraying the slight tremor that always followed high-altitude combat. "Speed and firepower give us advantages the Zero cannot match. What we need now is better accuracy in deflection shooting. The problem has become acute. Even our most experienced pilots are burning through ammunition without consistent results." Walsh paused, looking out across the muddy airfield where maintenance crews swarmed over parked Corsairs. The distinctive inverted gull wings of the fighters caught the morning light, their dark blue paint already showing the wear of operations in the harsh Pacific environment. Each aircraft represented a technological marvel, a fighting machine that exceeded anything marine aviation had previously fielded. Yet for all their speed and firepower, these magnificent aircraft remained limited by a fundamental problem that had plagued fighter pilots since the first aerial combats of the previous war. Through the scratched and oil-streaked plexiglass of his canopy, Walsh had spent the morning's mission watching this problem manifest repeatedly. He had escorted Navy SBD Dauntless dive bombers to their target, maintaining position above the vulnerable attack aircraft as they descended through Japanese airspace. The interception had come exactly as expected. Japanese A-6M0 fighters, rising from their base at Kahili, had attempted to break through the fighter escort to reach the bombers. What followed was a swirling engagement at 15,000 feet, Corsairs and Zeros locked in turning combat where split-second decisions determined survival. Walsh had witnessed 3 separate instances where less experienced pilots had achieved perfect positioning on enemy fighters, only to see their tracer rounds arc harmlessly behind fleeing targets. The mathematics of deflection shooting defeated even capable aviators. When 2 aircraft maneuver violently in 3 dimensions, hitting a target requires calculations that human minds simply cannot perform quickly enough. The pilot must aim not at the enemy aircraft's current position, but at where that aircraft will be when the bullets arrive. Those bullets, despite leaving the guns at tremendous velocity, still require time to cross the distance between aircraft. During that brief interval, a maneuvering target moves substantially, and the pursuing pilot must lead by exactly the correct amount. What Walsh and the thousands of other Marine and Navy pilots fighting across the Pacific could not yet know was that British engineers had already solved this fundamental problem. Working in facilities thousands of miles away, technicians at Ferranti Limited had developed a device that would transform aerial gunnery from an art requiring years of experience into a science that could be mastered in weeks. The Mark II gyroscopic gun sight, already proving its worth in European skies, incorporated spinning gyroscopes and precision optical systems to automatically calculate deflection angles. Within 12 months, an American version of this technology would arrive in the Pacific theater, fundamentally altering the mathematics of air combat and shifting the balance of power even further in favor of American fighter pilots. The Vought F-4U Corsair had entered combat operations with Marine Fighter Squadron 124 in February 1943, bringing unprecedented performance to marine aviation. The aircraft represented a quantum leap forward from the Grumman F-4F Wildcat that had borne the brunt of earlier fighting. Powered by the massive Pratt & Whitney R2800 double Wasp engine, an 18-cylinder radial power plant producing over 2,000 horsepower, the Corsair could exceed 400 miles per hour in level flight. This made it the first American single-engine fighter to break that threshold. a remarkable achievement that gave Marine pilots a decisive speed advantage over their Japanese opponents. The aircraft's distinctive appearance resulted from engineering compromises made to accommodate the enormous propeller required by such a powerful engine. The inverted gull-wing design allowed the main landing gear to be relatively short while still providing adequate clearance for the 13-foot, 4-inch diameter propeller. This configuration gave the Corsair its characteristic silhouette, instantly recognizable to both friend and foe across Pacific skies. The design also provided excellent aerodynamic efficiency, contributing to the aircraft's impressive speed and range capabilities. Armament consisted of 6 Browning M2 machine guns, 3 mounted in each wing panel outboard of the fold line. Each weapon fired 50 caliber ammunition, projectiles half an inch in diameter, weighing approximately 1 2/3 ounces. The guns cycled at a rate approaching 800 rounds per minute when functioning properly, though actual sustained fire rates were somewhat lower due to mechanical limitations and the need to prevent barrel overheating. When all 6 weapons fired simultaneously, the Corsair delivered a weight of fire exceeding 5 pounds per second, a devastating volume of metal that could destroy any Japanese aircraft with a brief burst. The challenge was making those bullets connect with maneuvering targets. Deflection shooting represented the single most difficult aspect of aerial combat, a problem that had confounded fighter pilots since the First World War. The fundamental difficulty arose from the relative motion of 2 aircraft, both traveling at high speed, both capable of rapid changes in direction and altitude. When a Corsair traveling at 400 miles per hour attempted to shoot a Zero executing evasive maneuvers at 300 miles per hour, the geometry became extraordinarily complex. Consider the physics involved in a typical engagement. 50 caliber bullets left the Corsair's machine guns at approximately 2,700 feet per second, a tremendous velocity that nonetheless required measurable time to reach a target. At a range of 500 yards, roughly 1,500 feet, those bullets required approximately half a second to arrive. During that half-second interval, a Zero executing a standard rate turn at 300 miles per hour would travel nearly 200 feet. The pursuing Corsair pilot had to aim his aircraft not at where the Zero currently was, but at the point in space where it would be when the bullets arrived. This calculation had to account for numerous variables. The target's speed affected how far it would travel during bullet flight time. The angle between the attacking aircraft and target aircraft, known as the deflection angle, determined how much lead was required. The range to target affected both bullet flight time and the amount the bullet would drop due to gravity during flight. Wind could push bullets off course, though this factor was typically negligible at close ranges. Most critically, both aircraft were pulling G-forces and changing direction continuously, meaning all these variables were constantly changing throughout the engagement. The human mind, for all its remarkable capabilities, struggles to perform such complex 3-dimensional calculations in the fractions of a second available during combat. The pilot must simultaneously fly his aircraft, track his target, monitor his altitude and airspeed, watch for other enemy aircraft, and somehow calculate the precise lead angle required to hit a violently maneuvering target. The cognitive load overwhelms even highly trained aviators. Most pilots developed rough intuitive methods, firing at what felt approximately correct based on experience and hoping for the best. The Mark 8 reflector sight, standard equipment on Corsairs through 1943 and most of 1944, provided no assistance whatsoever with this fundamental problem. The device was elegantly simple, consisting of an illuminated reticle projected onto a glass combining plate positioned in the pilot's line of sight. The reticle, typically a circular ring with a central dot and radiating crosshairs, appeared to float in space ahead of the aircraft. This optical illusion resulted from positioning the combining glass at a 45-degree angle, reflecting an illuminated image while simultaneously allowing the pilot to see through the glass to the world beyond. The reflector sight served one primary purpose. It showed the pilot exactly where his guns were aimed. The reticle indicated the bore axis of the aircraft, the imaginary line extending forward from the guns. If the pilot placed the reticle on a stationary target at close range, his bullets would strike that target. For any other situation, involving moving targets at varying ranges and deflection angles, the pilot was entirely on his own. The sight provided a reference point, nothing more. All deflection calculations remained the pilot's responsibility, performed mentally under enormous stress while pulling multiple G-forces that narrowed vision and made clear thinking difficult. Lieutenant Kenneth Walsh had mastered deflection shooting through exceptional natural ability combined with extensive practice. Flying with Marine Fighter Squadron 124, he had demonstrated the skills that separated great fighter pilots from merely adequate ones. On May 13, 1943, Walsh became the first Corsair pilot to achieve ace status, shooting down his 5th, 6th and 7th enemy aircraft during a single mission. This accomplishment resulted not from superior aircraft performance, which all Corsair pilots shared, but from Walsh's ability to instinctively calculate correct lead angles and fire at precisely the right moment. Walsh had learned through repetition and careful observation. He had developed an intuitive sense for how fast targets moved relative to his own aircraft, how much lead different deflection angles required, when to fire and when to hold his fire. This knowledge came from hundreds of hours in the cockpit, countless practice runs against towed target sleeves, and most importantly, from surviving actual combat encounters where mistakes meant death. Walsh could look at a maneuvering Zero, instantly assess its speed and direction, visualize where it would be half a second in the future, and place his reticle at that predicted point. His mind performed calculations that would challenge a trained mathematician, doing so in fractions of a second, while his aircraft pulled 4 G-forces and enemy tracers streaked past his canopy. Most Marine pilots lacked Walsh's exceptional gifts. The average pilot arriving in combat zones had logged perhaps 200 hours of total flight time accumulated over months of training in the United States. Of those 200 hours, perhaps 20 had involved actual gunnery practice, typically conducted against towed target sleeves that flew straight and level at predictable speeds. These training targets bore little resemblance to Japanese fighters piloted by experienced aviators determined to survive. Real combat involved violent maneuvers, rapid changes in speed and direction, multiple aircraft scattered across three-dimensional airspace, and overwhelming stress that made clear thinking nearly impossible. Against such opponents, average pilots struggled badly. Combat action reports from 1943 and early 1944 contain numerous instances of pilots expending all their ammunition, firing burst after burst at enemy aircraft without achieving a single confirmed hit. The bullets passed harmlessly behind fleeing targets because the pilot's mental calculations were consistently too slow. By the time the pilot's brain processed the target's position and calculated the required lead angle, the target had already moved. The pilot fired at where the target had been, not where it currently was, or where it would be when bullets arrived. This fundamental timing problem defeated even motivated, well-trained aviators who understood the theory of deflection shooting but could not execute the calculations quickly enough under combat stress. The British Royal Air Force had recognized this problem early in the European conflict. British fighter pilots, engaging German aircraft over England and France, encountered exactly the same difficulties that would later plague American pilots in the Pacific. Talented pilots like Douglas Bader and Stanford Tuck achieved impressive scores through natural ability and extensive experience. The majority of pilots, however, struggled to achieve consistent results. The RAF needed a solution that would improve the average pilot's effectiveness, not just rely on the exceptional abilities of natural marksmen. In 1941, Ferranti Limited, a British engineering firm with extensive experience in precision optical and mechanical systems, began producing the Mark II gyroscopic gun sight. This revolutionary device used principles from physics and mechanical engineering to automatically calculate deflection angles. The fundamental insight was elegantly simple. When an aircraft turns, spinning gyroscopes mounted inside the aircraft resist that turning motion due to conservation of angular momentum. By measuring how much the aircraft rotates relative to the stable gyroscopes, one can determine the aircraft's rate of turn. That rate of turn directly corresponds to the lead angle required to hit a target, because both the turning aircraft and the target aircraft are moving through the same airspace. The Mark II sight incorporated two independent gyroscopes measuring pitch and yaw rates. These gyroscopes spun continuously once powered, maintaining their orientation in space regardless of how the aircraft maneuvered around them. Precision gears and mirrors measured the relative motion between the aircraft and the stable gyroscopes, translating that motion into movements of the aiming reticle. The reticle automatically positioned itself ahead of the target by exactly the correct amount of lead required for the current rate of turn. The pilot simply had to place that computed reticle on the target and fire. The bullets would arrive precisely where the sight predicted. Royal Air Force pilots using the Mark II gyroscopic sight reported dramatic improvements in combat effectiveness. Spitfire pilots who had previously struggled with deflection shooting suddenly found themselves hitting targets on their first firing pass. The sight eliminated the need for complex mental calculations, allowing pilots to focus their attention on tactics, situational awareness, and aircraft handling rather than geometry. Combat reports documented significantly improved kill ratios among squadrons equipped with gyroscopic sights compared to those still using reflector sights. The United States recognized this technology's tremendous potential immediately upon learning of British developments. American military observers in England sent detailed technical reports describing the Mark II sight's capabilities and its impact on RAF combat effectiveness. These reports reached American aviation leadership at a critical moment. American fighter pilots were beginning to engage Japanese forces in the Pacific, and early combat reports indicated the same deflection shooting problems that had plagued British pilots earlier in the war. The United States Army Air Force and United States Navy both moved quickly to acquire gyroscopic gun sight technology. Rather than developing entirely new designs from scratch, which would have consumed precious time, American military procurement officers contracted with Sperry Gyroscope Company to produce American versions of the British Mark II sight. Sperry, already manufacturing bomb sights, navigational systems, and various other precision instruments for military aviation, possessed the technical expertise and manufacturing facilities necessary to produce gyroscopic gun sights in the enormous quantities required to equip thousands of American fighters. Sperry's main manufacturing facility in Lake Success, New York, expanded dramatically to meet wartime production demands. At peak operations, the facility employed over 20,000 workers, turning out gyroscopic gun sights alongside bomb sights, fire control systems, radar components, and navigational equipment. The workforce included skilled machinists, optical technicians, assembly workers, inspectors, and support personnel. Many positions were filled by women, taking jobs in precision manufacturing previously considered unsuitable for female workers. These women proved highly capable at the exacting work required to produce precision optical and mechanical instruments. The American version of the British Mark II sight received different designations depending on which service branch would use it. The United States Army Air Force designated their version the K-14, while the United States Navy and Marine Corps called theirs the Mark 18. Both were essentially identical to the British Mark II, with minor modifications to accommodate American manufacturing techniques, American measurement standards, and integration into American aircraft cockpits. The core technology, the fundamental principles of gyroscopic deflection computation, remained unchanged from the British original. The Mark 18 gyroscopic gun sight was substantially larger and heavier than the simple reflector sight it replaced. Where the Mark 8 reflector sight was a compact unit weighing perhaps 5 pounds and requiring minimal cockpit space, the gyroscopic sight system weighed approximately 12 pounds and occupied significantly more volume. This additional bulk resulted from the complexity of the internal mechanisms. Inside the housing were two independent gyroscopes measuring pitch and yaw, each consisting of a rapidly spinning rotor mounted in precision gimbals that allowed it to maintain orientation regardless of aircraft movement. The gyroscopes required electric motors to spin them up to operational speed and maintain that speed throughout flight operations. Precision gears translated gyroscope motion into mirror movements. Optical components projected the computed aiming reticle onto the combining glass where the pilot could see it. Installing the Mark 18 in existing Corsair aircraft required significant cockpit modifications. The site occupied more space than the reflector site, necessitating adjustments to instrument panel layouts. Electrical connections had to be installed to power the gyroscope motors. Control mechanisms had to be integrated into existing cockpit controls, particularly the throttle lever, which received a twist grip for range adjustment. These modifications were time-consuming and required skilled aircraft mechanics, limiting how quickly existing aircraft could be retrofitted with the new site. Sperry engineers had designed the Mark 18 to be as robust as possible given the challenging operating environment. Fighter aircraft cockpits subjected equipment to tremendous stresses. Temperature extremes ranged from sub-zero at high altitude to over 100 degrees Fahrenheit on tropical airfields. Vibration from the powerful engine transmitted through the airframe continuously. Combat maneuvers imposed G-forces that stressed every component. The site had to function reliably despite these harsh conditions, maintaining its delicate alignment and continuing to compute accurate deflection angles, even while the aircraft pulled 4 or 5 G-forces in violent turns. The Mark 18's design incorporated several features intended to ensure reliability under combat conditions. The gyroscopes were mounted in shock-absorbing housings to isolate them from engine vibration. Electrical connections used military-grade connectors designed to resist vibration and corrosion. The optical system used high-quality glass elements that could withstand temperature changes without losing alignment. Assembly procedures included extensive testing at each stage, with inspectors verifying that every component met exacting specifications before final installation. Despite these quality control measures, the complexity of the Mark 18 meant it required more maintenance than the simple reflector sight. Gyroscopes eventually wore out and required replacement. Electrical motors failed and needed repair. Optical elements became misaligned and required readjustment. Squadron maintenance personnel received specialized training in Mark 18 maintenance and repair procedures. Spare parts were stocked at maintenance facilities throughout operational theaters, ensuring that aircraft with failed gun sites could be returned to operational status quickly. The Mark 18's operational use required pilots to understand its capabilities and limitations. The site featured 2 distinct reticles visible to the pilot simultaneously. On the left side of the field of view, a fixed illuminated cross indicated where the aircraft's guns were actually pointed, providing a reference for the bore axis. This fixed reticle remained stationary relative to the aircraft, moving only when the entire aircraft changed orientation. On the right side, a gyroscopically stabilized reticle consisting of a central circle surrounded by 6 diamond-shaped pips showed the computed aiming point. This moving reticle responded to the aircraft's motion, automatically positioning itself to indicate where the pilot should aim to hit a target. Operating the Mark 18 required the pilot to perform several steps before engaging a target. First, he had to set the target's wingspan using a control dial on the site itself. This dial allowed selection from a range of predetermined values corresponding to known Japanese aircraft types. The Mitsubishi A6M0, the most common opponent in Pacific combat, had a wingspan of 36 feet for standard variants. The Nakajima Ki 43 Oscar, another frequently encountered fighter, had a wingspan of 35 feet 8 inches. Bombers had substantially larger wingspans, with the Mitsubishi G4M Betty measuring 82 feet. Setting the correct wingspan was crucial because the site used this information to calculate range in the next step. With wingspan selected, the pilot then had to set range using a twist grip control integrated into the throttle lever. As the pilot rotated this grip, the 6 diamond-shaped pips of the ranging reticle expanded or contracted. The pilot adjusted this ranging reticle until it matched the apparent wingspan of the target aircraft, as seen through the sight. When the diamonds exactly bracketed the target's wingtips, the sight knew precisely how far away the target was. This mechanical range-finding system was ingenious in its simplicity, requiring no electronics or complex calculations, just the pilot's visual judgment to match reticle size to target size. With wingspan and range properly set, the gyroscopes took over the deflection calculation. As the pilot maneuvered his aircraft to track the target, the gyroscopes measured the aircraft's rate of turn in both pitch and yaw. The site's mechanical computer translated these turn rates into the precise lead angle required for the current engagement geometry. The moving reticle automatically positioned itself ahead of the target by exactly this calculated amount. The pilot simply had to place that computed reticle on the enemy aircraft and press the trigger. The bullets would follow a trajectory that intercepted the target at the predicted point, regardless of how complex the maneuvering might be. Production of the K-14 and Mark 18 began during spring 1944, as Sperry's manufacturing facilities ramped up to full production capacity. The United States Army Air Force received initial priority for equipment deliveries, with P-51 Mustangs and P-47 Thunderbolts serving in the European theatre receiving K-14 installations beginning in August 1944. The Navy and Marine Corps followed shortly after, with F-4U Corsairs and F-6F Hellcats scheduled for Mark 18 retrofits through the fall and winter of 1944. The first Corsair squadrons to receive the Mark 18 were those preparing for carrier operations, a significant milestone in Corsair operational history. The F-4U had originally been designed as a carrier-based fighter, intended to operate from the decks of Essex-class fleet carriers. However, early carrier qualification trials revealed serious problems. The Corsair's long nose blocked the pilot's forward view during landing approaches, making carrier landings extremely difficult. The aircraft's high landing speed and tendency to bounce on touchdown created additional hazards. Most critically, the landing gear's stiff oleo struts caused the aircraft to bounce violently if it landed hard, often resulting in the landing gear collapsing or the aircraft going over the side of the carrier deck. These problems led the Navy to conclude that the Corsair was unsuitable for carrier operations, at least in its current configuration. Marine Corps squadrons, operating from land bases throughout the Pacific, gladly accepted the aircraft that Navy carrier squadrons could not use. Marines flew the Corsair with great success from rough airfields carved out of jungle, proving the aircraft's combat effectiveness even if carrier operations remained problematic. By late 1944, however, engineering modifications and improved pilot training techniques had resolved many of the carrier landing difficulties. The introduction of the Malcolm Hood modification improved visibility. Adjustments to the oleo strut settings reduced the bounce tendency. Most importantly, pilots developed specific techniques for carrier approaches that compensated for the Corsair's challenging handling characteristics. Marine squadrons VMF-124 and VMF-213 became the first marine fighter units assigned to fleet carriers, preparing to bring the F-4U into carrier-based combat. Both squadrons received their Mark 18-equipped Corsairs during training at Marine Corps Air Station Santa Barbara in the fall of 1944. Pilots underwent extensive training in the new gun sights operation, learning procedures for setting wingspan, adjusting range, and interpreting the gyroscopic reticle's indications. Flight training included practice interceptions against target aircraft, allowing pilots to experience how the sight behaved during actual tracking situations. The training emphasized smooth, steady tracking, as the gyroscopes required consistent turn rates to compute accurate deflection angles. Lieutenant Robert McClurg, assigned to the reformed Marine Fighter Squadron 214, received his Mark 18-equipped Corsair in January 1945. VMF-214 was being reconstituted after the original squadron, led by the legendary Major Gregory Boyington, had been withdrawn from combat in early 1944. The new VMF-214 would carry on the traditions of the original squadron while incorporating the latest technology and tactics developed over 2 years of Pacific combat. McClurg had already scored several victories during earlier deployments using standard reflector sights, giving him a basis for comparison when evaluating the new gyroscopic technology. In a letter to his family, later preserved in Marine Corps historical archives, McClurg described the Mark 18 as representing the difference between skilled guesswork and mechanical certainty. The device, he wrote, compressed years of deflection shooting experience into a few hours of training. A pilot who understood how to operate the sight could achieve accuracy comparable to veterans with hundreds of combat hours. Japanese naval aviation intelligence first became aware of American gyroscopic gun sight technology in late 1944 through multiple sources. Technical intelligence officers analyzed wreckage from downed American fighters, recovering components of the Mark 18 sight from crashed Corsairs. Interrogation of captured documents provided additional information about American fire control developments. Most significantly, debriefings of Japanese pilots who had survived encounters with Mark 18-equipped aircraft revealed disturbing patterns. These pilots reported that American shooting accuracy had improved dramatically, with American pilots achieving hits even during violent evasive maneuvers that should have made accurate shooting impossible. Japanese technical analysts who examined recovered Mark 18 components quickly understood the threat this technology represented. The gyroscopic deflection computation system largely eliminated human error in deflection shooting, the primary weakness that Japanese tactical doctrine had exploited throughout earlier Pacific air battles. Japanese fighters had survived against numerically superior American forces by using their superior maneuverability to force American pilots into difficult high-deflection shots, where human calculation errors provided some margin of safety. Against Mark 18-equipped Corsairs, that tactical advantage evaporated. Any American pilot who could hold a tracking solution long enough to set range would score hits, regardless of how violently the Japanese pilot maneuvered. Japanese fighter tactics were immediately modified across all naval aviation units operating in the Pacific. New standing orders emphasized avoiding prolonged turning engagements with American fighters at all costs. The revised doctrine called for hit-and-run attacks, diving from altitude to make a single high-speed pass before extending away using superior energy. Japanese pilots were explicitly instructed not to engage in sustained dogfights where American technological advantages in fire control could be fully exploited. This tactical shift acknowledged an uncomfortable reality that Japanese aviation leadership had been reluctant to accept. Japanese fighters could no longer rely on maneuverability alone to survive against opponents equipped with technologically superior weapon systems. December 1944 brought a watershed moment in Corsair operational history. Marine Fighter Squadron 124, commanded by Major William Millington, became the first Marine fighter unit to operate from a fleet carrier when they joined USS Essex at Ulithi Atoll. VMF-213, commanded by Major David Marshall, joined simultaneously, bringing a total of 48 F-4U Corsairs to carrier-based operations. Both squadrons were fully equipped with Mark 18 gyroscopic gun sights, representing the cutting edge of American aviation technology deployed aboard the most powerful warships in human history. The Essex Air Group departed Ulithi in January 1945 for combat operations against Japanese-held territories in Formosa and the Philippines. Marine Corsair pilots flew combat air patrol missions protecting the carrier task force, bomber escort missions accompanying Navy strike aircraft, and fighter sweep missions seeking out Japanese aircraft on the ground and in the air. The Mark 18 sight proved invaluable during these varied operations, providing consistent accuracy across different mission profiles and engagement scenarios. pilots engaging Japanese interceptors during bomber escort missions reported significantly improved hit rates compared to their previous combat experiences using reflector sights. Combat action reports from January and February 1945 document numerous instances where pilots achieved confirmed kills with their initial burst, a level of first-pass lethality that had been uncommon in earlier engagements. The difference became most apparent during defensive combat air patrol missions, where Corsairs intercepted Japanese aircraft attacking the task force. In these high-stress situations, where hesitation or missed shots could result in Japanese bombers reaching American ships, the Mark 18's reliability proved crucial. The sight's capability to calculate accurate deflection from any angle transformed constrained tactical situations into opportunities. During bomber escort missions, Corsairs typically maintained formation positions relative to the bombers they were protecting. These positions often prevented ideal attack geometry when Japanese interceptors appeared. With reflector sights, pilots had been forced to maneuver away from their escort positions to achieve 6 o'clock stern attacks, the only geometry where deflection shooting was relatively simple. This maneuvering took time and temporarily left bombers more vulnerable. The Mark 18 allowed pilots to engage immediately from whatever angle they currently occupied, achieving hits from beam attacks, high deflection overhead passes, and other geometries that would have been impractical with older fire control systems. February 1945 brought Operation Detachment, the assault on Iwo Jima, an 8-square-mile volcanic island that would become one of the bloodiest battles in Marine Corps history. While Marine infantrymen fought savage ground combat against deeply entrenched Japanese defenders, Marine Corsair squadrons provided continuous air cover for the invasion force. Multiple squadrons operated from escort carriers positioned off the island, maintaining combat air patrols from dawn to dusk throughout the battle's 36-day duration. Mark 18-equipped Corsairs demonstrated their effectiveness during defensive missions against Japanese air attacks. Though the scale of Japanese aerial opposition at Iwo Jima was relatively limited compared to later operations at Okinawa, the attacks that did occur were pressed home with determination and skill. Pilots intercepting incoming Japanese strike packages consistently achieved kills at ranges and deflection angles that would have been difficult with reflector sights. The gyroscopic sight's automatic deflection calculation allowed pilots to engage multiple targets during single interceptions, achieving 2 or 3 kills where they might previously have managed only 1. Squadron commanders noted in operational reports that pilots with relatively limited combat experience were achieving effectiveness comparable to veterans, primarily due to improved fire control. The Mark 18 had compressed the learning curve for aerial gunnery, allowing newer pilots to contribute meaningfully to combat operations far sooner than would have been possible without the technological assistance. This democratization of combat effectiveness had strategic implications, as it meant American squadrons maintained high combat power even as experienced pilots were rotated home and replaced by newer aviators fresh from training. March 1945 saw the continuation of carrier operations against the Japanese home islands. Marine Fighter Squadron 214, operating aboard USS Franklin, participated in strikes against Japanese airfields and military installations on Kyushu. On March 19th, disaster struck the Franklin when a Japanese bomber penetrated the task force's defensive screen and scored hits with 2 bombs. The resulting explosions and fires killed over 700 personnel aboard the carrier, including 32 members of VMF 214. The squadron suffered devastating losses, losing pilots and ground crew to the inferno that consumed the carrier's hangar deck. The survivors of VMF 214 faced a grim reality. Their carrier was crippled, their aircraft destroyed, their comrades dead. Franklin managed to survive through extraordinary damage control efforts and eventually limped to safety, but the cost had been terrible. The disaster highlighted the brutal mathematics of carrier aviation, where a single successful enemy attack could inflict casualties exceeding those of an entire infantry battalion. Despite these losses, Marine Corsair squadrons continued their mission, replacing lost aircraft and pilots and returning to combat operations against Japan. April 1945 brought Operation Iceberg, the invasion of Okinawa, the largest amphibious assault in Pacific War history, and the bloodiest campaign American forces would fight against Japan. The battle would continue for 82 days, resulting in over 50,000 American casualties and providing a terrifying preview of what invading the Japanese home islands would cost. From the beginning, American naval forces supporting the invasion faced unprecedented aerial assault. Japanese commanders, recognizing that conventional air tactics could not defeat American forces, had embraced kamikaze operations as their primary aerial weapon. Thousands of aircraft, many flown by minimally trained pilots, were thrown against American ships in waves of suicide attacks that continued day after day. Marine Corsair squadrons played a crucial role in defending against these attacks. Pilots flew continuous combat air patrols, intercepting incoming kamikaze formations at maximum range from the fleet. The psychological and physical demands of these missions tested pilots to their limits. Combat air patrol stations were maintained at considerable distance from the fleet, requiring pilots to remain alert for hours while watching empty sky. When Japanese formations appeared, identified by radar controllers, pilots had to intercept quickly while conserving enough fuel to return to their carriers. The Mark 18 proved particularly effective against kamikaze aircraft. Unlike conventional fighter tactics, where Japanese pilots used their aircraft's maneuverability to evade, kamikaze pilots flew straight toward their targets, making no attempt at evasion until the final moments before impact. This made them ideal targets for the gyroscopic gun sight. Pilots could acquire incoming kamikazes early, set range using the sight's ranging reticle, and achieve devastating first-burst accuracy. The Mark 18's ability to compensate for deflection meant pilots could engage kamikazes from any angle, shooting them down even when intercepting from the beam or in head-on passes. Combat air patrol missions during the Okinawa campaign resulted in hundreds of Japanese aircraft destroyed. While precise statistics specifically attributing kills to Mark 18-equipped aircraft versus those still using reflector sights are not available in declassified operational records, squadron reports consistently noted improved combat effectiveness among units equipped with gyroscopic sights. The ability to achieve reliable kills on first pass became critical during periods of mass kamikaze attacks, when dozens of Japanese aircraft might approach simultaneously. The psychological impact on Japanese pilots who survived encounters with Mark 18-equipped Corsairs extended beyond simple tactical disadvantage. Post-war interviews with Japanese aviators who flew during 1945 reveal profound demoralization caused by American technological superiority. The experience of executing violent evasive maneuvers, using every bit of their aircraft's capability and their own skill, only to be hit regardless of their efforts, created a sense of helplessness that traditional training had not prepared them for. Japanese pilots had been taught that superior skill and aircraft handling could overcome material disadvantages. The Mark 18 demonstrated that technological advantages could neutralize skill entirely. The certainty of being hit once an American pilot achieved a tracking solution eliminated hope that had sustained Japanese fighter pilots through increasingly desperate circumstances. Maneuverability, the foundation of Japanese fighter doctrine since the war's beginning, could no longer save them. Experience provided no meaningful advantage against automated fire control systems. The only escape was avoiding engagement entirely, a tactical impossibility when assigned to defend against attacking bombers or protect Japanese surface forces. The Mark 18's technical operation represented a remarkable achievement in mechanical computing during an era before electronic computers existed outside of research laboratories. The system performed complex calculations using purely mechanical linkages, precision gears, and carefully designed mirror assemblies. No transistors, no integrated circuits, no digital processing, just precisely machined metal parts working together to solve differential equations in real time. The gyroscopes at the heart of the system spun continuously once the sight was powered from the aircraft's electrical system. These gyroscopes, each about the size of a pocket watch, consisted of a precisely balanced rotor spinning at thousands of revolutions per minute. The rotor was mounted in a gimbal assembly that allowed it to maintain its orientation regardless of how the aircraft moved. This stability resulted from conservation of angular momentum, a fundamental principle of physics stating that a spinning object resists changes to its axis of rotation. When the aircraft turned, the gyroscope housing rotated, while the gyroscope rotor remained pointed in its original direction. Precision gears measured this relative motion between housing and rotor, translating it into rotation of mirror assemblies. These mirrors redirected the projected aiming reticle, moving it across the pilot's field of view by precisely the amount needed to compensate for the aircraft's turn rate. The mechanical beauty of this system lay in its directness. Physical laws of gyroscopic motion were directly translated into mirror positions through elegant mechanical linkages requiring no intermediate calculation steps. The manufacturing challenge was producing these systems in quantity while maintaining the tolerances required for accurate operation. Each Mark 18 required dozens of precisely machined components. The gyroscope rotors had to be balanced to tolerances measured in thousandths of an inch to prevent vibration that would degrade accuracy. Bearing surfaces had to be manufactured to extreme precision to ensure smooth operation under high-G combat maneuvering. Mirrors required optical quality surfaces with precisely controlled curvature. Gear teeth had to mesh with minimal backlash to prevent errors in translating gyroscope motion to mirror position. Sperry's manufacturing facilities represented the pinnacle of American precision manufacturing capability during the 1940s. The company employed thousands of skilled machinists, tool and die makers, optical technicians, and quality control inspectors. Training programs brought workers up to the skill levels required for producing precision instruments. Specialized machine tools were developed specifically for manufacturing gyroscope components. Quality control procedures tested every component at multiple stages of production, ensuring that defective parts were identified and rejected before final assembly. The modular design philosophy incorporated into the Mark 18 reflected practical considerations about military logistics and field maintenance. In combat zones, repair facilities were primitive compared to factory conditions. Maintenance had to be possible using basic tools under difficult conditions. The Mark 18 was designed so that major sub-assemblies could be replaced as units rather than requiring complete site replacement. If a gyroscope failed, technicians could remove and replace just that gyroscope assembly. If mirrors became misaligned, that optical module could be swapped out. This modularity meant that one damaged site could provide spare parts for repairing several others, extending the useful life of the equipment in the field. Spare parts were distributed throughout the Pacific Theater supply chain. Aircraft tenders, the specialized ships that supported carrier operations, carried substantial stocks of Mark 18 components. Major shore establishments maintained repair facilities where damaged sites could be completely rebuilt. This logistics infrastructure ensured that mechanical failures did not result in prolonged aircraft downtime. A Corsair with a failed gun sight could typically be returned to operational status within 24 hours, sometimes much faster if the problem was a simple component swap. Training programs developed to teach pilots effective Mark 18 operation emphasized practical skills over theoretical understanding. Pilots needed to know how to use the sight, not how it worked internally. Ground school instruction covered the basic operating procedures. Set wingspan for the target type. Adjust range until the diamonds bracket the target's wings. Place the computed reticle on the target. These steps were practiced repeatedly until they became automatic, requiring no conscious thought during the chaos of combat. Flight training reinforced these procedures through practice intercepts. Instructor pilots flew target aircraft while students practiced tracking and ranging. The training emphasized smooth, steady tracking rather than jerky corrections. The gyroscopes needed consistent input to compute accurate deflection. If a pilot flew erratically, executing sudden reversals and wild maneuvers, the gyroscopes would lag, and the sight's accuracy would temporarily degrade. Skilled pilots learned to maintain smooth pursuit curves, allowing the site's mechanical computer to operate optimally. Training also covered limitations and edge cases. The gyroscopes required several seconds to stabilize after violent maneuvers or initial power-up. If a pilot snapped into a hard turn immediately after engaging the site, the deflection computation would be inaccurate until the gyroscopes caught up. Pilots learned to recognize when the site had achieved stable operation, waiting for the reticle to settle before taking shots. This awareness of the site's dynamic response became second nature through practice. Another important limitation involved very close-range engagements. The Mark 18's ranging system worked well at ranges from about 200 to 800 yards. At closer ranges, targets appeared too large for accurate ranging using the diamond reticle. At longer ranges, targets were too small. Pilots learned to recognize these boundary conditions and adjust their tactics accordingly. Most aerial gunnery occurred within the site's optimal range band anyway, but understanding the limitations prevented mistakes. Despite these minor limitations, the Mark 18 represented revolutionary progress in aerial gunnery. For the first time in aviation history, average pilots could achieve accuracy levels previously reserved for natural marksmen. The site didn't eliminate the need for skill entirely. Pilots still had to fly their aircraft effectively, maintain situational awareness, make tactical decisions, and manage their energy state. But the actual mechanics of shooting, the hand-eye coordination and spatial calculation that had been so difficult, became vastly more manageable. The cumulative impact on combat operations was substantial, even if exact quantification remains difficult from available records. The F-4U Corsair achieved an overall kill ratio of 11-1 during World War II, with 2,140 confirmed air combat victories against 189 losses to enemy aircraft across 64,051 operational sorties. These impressive statistics represent the combined performance of aircraft equipped with both reflector sights and gyroscopic sights throughout the entire war. Separating the specific contribution of the Mark 18 from other factors like pilot training quality, tactical doctrine, aircraft performance, and numerical superiority would require access to detailed mission reports that remain classified or were never preserved in sufficient detail. What can be documented from available sources is consistent pilot testimony. Every pilot who flew combat missions with both sight types reported that the Mark 18 made deflection shooting more reliable and less dependent on natural talent. Squadron historical records, pilot memoirs published decades later, and oral history interviews conducted by military historians all tell the same story. The gyroscopic sight worked. It made hitting maneuvering targets easier. It allowed less experienced pilots to achieve results comparable to veterans. These qualitative assessments, coming from hundreds of independent sources over many decades, provide strong evidence of meaningful combat effectiveness, even absent precise statistical proof. The broader context of American technological superiority in the Pacific War helps frame the Mark 18's contribution. American forces enjoyed advantages in radar technology, providing early warning and fighter direction that Japanese forces could not match. American radio communications enabled coordinated operations across entire task forces. American proximity-fused anti-aircraft ammunition created defensive barriers around ships that made Japanese attack extremely costly. American industrial production simply overwhelmed Japanese capacity, producing thousands of aircraft where Japan produced hundreds. The Mark 18 fit into this larger pattern of systematic technological advantage. It wasn't a wonder weapon that single-handedly determined the war's outcome. It was one component of a comprehensive technological superiority that manifested across every domain of warfare. Each individual technology provided incremental advantages. Taken together, these advantages created a synergistic effect that made American victory inevitable, barring catastrophic strategic errors. The legacy of the Mark 18 extended well beyond its direct combat application during World War II. The site's development established important precedents for how military technology could be developed and deployed. The process demonstrated that effective weapons could be created through international collaboration, adapting British innovations for American production, rather than insisting on purely domestic developments. This pragmatic willingness to adopt good ideas, regardless of origin, would serve American military aviation well throughout subsequent decades. The procurement process also validated the importance of rapid fielding. Sperry moved from initial contract to production deliveries in under 12 months, an impressively short timeline for introducing complex technology. Modern defense acquisition processes typically require years or decades for comparable technology transitions. The Mark 18 program showed that when priorities were clear and bureaucratic barriers minimized, American industry could respond with remarkable speed. Manufacturing techniques developed for Mark 18 production had lasting impact beyond the specific device. Sperry's modular design philosophy, where complex systems were broken into sub-assemblies that could be manufactured independently and then integrated, became standard practice for precision military equipment. This approach enabled the massive production scales that gave American forces their material superiority. Similar techniques were later applied to radar systems, fire control computers, and eventually electronics, creating an industrial base capable of producing sophisticated equipment in quantities impossible for other nations. The pilots who flew with Mark 18 sites formed a bridge generation, experiencing both traditional instinctive aerial combat and emerging technology-assisted engagement. Many continued military careers after World War II ended, flying jets in Korea, commanding squadrons, and serving in staff positions where they influenced tactical doctrine for decades. Their experiences shaped how the military thought about integrating technology with human operators, finding the right balance between automation and pilot judgment. Lieutenant Kenneth Walsh, who had become the first Corsair ace in May 1943, using nothing but a reflector sight and exceptional natural ability, ended the war with 21 confirmed victories. He received the Medal of Honor for extraordinary heroism during combat operations on August 15, 1943, when he attacked a formation of 50 Japanese aircraft despite heavy damage to his own Corsair. Walsh survived the war and remained in the Marine Corps, eventually retiring as a lieutenant colonel after serving through the Korean War era. His career spanned the complete transformation of aerial warfare from instinctive dogfighting to technology-dominated engagement. Lieutenant Robert McClurg, who flew with VMF 214 during the squadron's second deployment in 1945, survived the war with 7 confirmed victories. He remained in military service through 1965, retiring as a colonel after 25 years of service. In retirement, McClurg wrote extensively about his experiences, emphasizing that technology like the Mark 18 improved effectiveness without eliminating danger. The sight made deflection shooting more reliable, but combat remained deadly regardless of equipment advantages. Countless factors beyond fire control accuracy determined survival. Situational awareness, energy management, tactical judgment, and simple luck all mattered as much as the ability to shoot accurately. The story of the Mark 18 gyroscopic gun sight concludes not with dramatic endings, but with gradual evolution into more sophisticated systems. As jet aircraft replaced propeller fighters during the 1950s, new fire control technologies replaced gyroscopic sights. Radar ranging eliminated manual range setting. Electronic computing replaced mechanical linkages. The Mark 18 didn't suddenly fail or become useless. It simply became outdated as faster aircraft, longer engagement ranges, and guided missiles created requirements that purely mechanical systems couldn't meet. Some Mark 18 sites remained in service aboard Corsairs flying close air support missions during the Korean War from 1950 to 1953. These aircraft proved remarkably effective in ground attack roles, their heavy weapons and rugged construction ideal for supporting infantry against North Korean and Chinese forces. The Mark 18 sites aboard these aircraft continued functioning reliably, demonstrating the robust design that had allowed the system to survive years of carrier operations and combat stress. Other Mark 18 units entered storage as aircraft were retired, eventually being scrapped or preserved in museums. A few examples survive today in aviation museums and military history collections, tangible links to an era when the most advanced computers were made of spinning gyroscopes and precisely cut gears rather than silicon chips. These preserved examples allow modern visitors to appreciate the mechanical ingenuity of 1940s engineering, the sophisticated solutions that could be achieved without electronics. The Mark 18's legacy lives on in principles rather than physical devices. Every modern fire control system, regardless of sophistication, traces its intellectual heritage to devices like the Mark 18 that first automated fundamental aiming calculations. The engineers who designed and built gyroscopic gun sights contributed knowledge that extends far beyond their specific technical achievements. They proved complex calculations could be performed mechanically with sufficient reliability for combat use. They demonstrated that human-machine interfaces could function under extreme stress. They showed sophisticated technology could be manufactured at scale and maintained under primitive field conditions. The pilots who flew with Mark 18 sights contributed their own lasting legacy through the tactical doctrine they developed. They demonstrated that humans could effectively partner with automated systems, neither becoming completely dependent on technology nor rejecting it as unnecessary. This balanced approach to human-machine teaming became increasingly important as automation extended into more aspects of military operations. The lessons learned during the Mark 18 era remained relevant as computers, guided weapons, and autonomous systems progressively changed how wars were fought. For modern military aviation, the Mark 18 represents an important milestone in the progression from purely manual weapon aiming to fully automated engagement. The sight occupied a middle ground where human judgment and machine calculation worked together. The pilot still made tactical decisions about when and what to shoot. The sight simply helped execute those decisions more effectively. This collaborative model proved more successful than either extreme of pure manual operation or complete automation. The statistical record of World War II Corsair operations provides broader context for understanding the Mark 18's contribution. Marine and Navy Corsair squadrons flew tens of thousands of sorties between 1943 and 1945, achieving the impressive 11-to-1 kill ratio that established the Corsair among the war's most successful fighters. This success resulted from multiple factors working in combination, not any single technological advantage. The Corsair's substantial speed advantage over Japanese fighters allowed American pilots to control engagement geometry, choosing when to fight and when to disengage. Japanese fighters could not catch a fleeing Corsair, giving American pilots tactical flexibility impossible for their opponents. The Corsair's rugged construction absorbed battle damage that would destroy lighter Japanese aircraft. American pilots routinely returned to base with significant damage, while similar hits disabled Japanese fighters. The Corsair's heavy armament of 650 caliber machine guns delivered overwhelming firepower when hits were achieved. The Mark 18 gyroscopic sight amplified these existing advantages by making the Corsair's firepower easier to deliver accurately. The sight didn't create the Corsair's superiority. The aircraft was already highly effective with reflector sights. The Mark 18 enhanced what was already a formidable weapons system, making good pilots better and average pilots more effective. The final assessment must acknowledge both what can be documented and what remains uncertain. Official records confirm the Mark 18 was produced in substantial numbers and equipped numerous squadrons during 1944 and 1945. Combat reports indicate improved accuracy among pilots using gyroscopic sights. Pilot testimony uniformly describes the Mark 18 as a significant improvement. What cannot be precisely quantified is the exact statistical improvement in combat effectiveness, separated from all other factors that influenced aerial combat outcomes. What remains absolutely clear is that the Mark 18 represented meaningful technological progress that provided practical advantages to pilots who used it. It exemplified American industrial capacity, systematic problem-solving, and willingness to adopt effective technology regardless of origin. The site succeeded because it was practical, reliable, and adequately effective. These characteristics, perhaps less dramatic than revolutionary breakthroughs, define technology that actually makes a difference in the real world. The story of the Mark 18 is ultimately a story of people solving problems through organized effort. British scientists identified fundamental principles. British engineers developed working prototypes. American procurement officers recognized the technology's potential. American engineers adapted the design for mass production. American factory workers manufactured tens of thousands of units. American logistics personnel delivered equipment where needed. American maintenance technicians kept systems operational. American pilots used the technology effectively. American commanders integrated it into successful operations. Each group contributed essential elements. Without any single contribution, the program would have failed. This collaborative nature of technological success deserves emphasis in an era that often celebrates individual genius. Individual brilliance mattered, but organized, competent effort across many people and organizations mattered more. The Mark 18 resulted from thousands of individuals doing their jobs conscientiously. That collective effort determined success more than any individual contribution. For the Corsair pilots who flew with Mark 18 sites during 1945, the device was simply an effective tool that made a difficult job somewhat easier. It didn't eliminate danger or guarantee survival. Combat remained deadly despite technological advantages. But the site improved their odds in a profession where